Welcome back to the short series on the fundamentals of control engineering. In this video, we introduce linear dynamical systems. Linear systems are a very special class of dynamical systems, and in particular, we will focus on linear time invariant systems during this course. An LTI system, as they're called, is a time invariant system that is also a linear system, which means that the superposition principle applies. As a reminder, we have seen that for time invariant system, we can always write down an explicit representation that looks like this. What we mean with this expression, when we write that u is considered over the interval 0 to t minus t naught, is that we can always set t naught equals 0, since our system is invariant under translations in time, and we can consider u as a signal that starts at 0 and is evaluated over the interval that goes up to the current elapsed time, t minus t naught. Now, as we have just said, a linear system is a system for which the superposition principle holds. This principle states that if we have two different solutions to our system, so let's say we have x1 of t under the action of u1 and x2 of t under the action of u2, and starting from, of course, two different initial points, x1 naught and x2 naught, then composition of these trajectories in the form alpha 1 x1 plus alpha 2 x2 will also be a solution of our system under the inputs alpha 1 u1 plus alpha 2 u2. Note that you can both scale the input to obtain a scaled version of the state, or you can also combine multiple inputs to obtain a combined version of the states which correspond to each of them. So imagine we have two different signals. Let's say that one of our inputs is, for instance, a step, which produces a response which looks like this in the state. And then assume we have another input, which is maybe a sinusoid, which produces another response in the state, which is also approximately sinusoidal. Then if we feed the signals to our system, we can either scale each of them. So if we have double this constant, for example, we will get double this signal. Or we can combine them so that the sum of the inputs will give us the sum of the states. In terms of the implicit representation of the system, we have, again, x dot equals. And again, if we combine the inputs, we obtain a combined version of both the states and the outputs. Note that here we drop the dependency on time for brevity. Linear systems also admit a very handy representation, which is known as the state space representation, which has the standard form x dot equals some matrix A times the vector x plus some other matrix B times the vector of inputs u, and the output y is also linear in x and u through some other matrices C and D. And let's give dimensions to these quantities. So we assume x is an n-dimensional vector, u is an m-dimensional vector, and y is a p-dimensional vector, and then the matrices will have dimensions accordingly. For linear systems, such a representation always exists in virtue of the representation theorem for linear functions. Such a theorem states that if we take a generic function g that goes from a space, let's say r to the n, into another space, let's say r to the m, and g is linear, then there exists a matrix capital G of suitable dimensions such that the application of G to a vector x is equivalent to the product of G times this vector. And this is true for each x in R to the n. The proof of this result is quite easy, so let's quickly go through it. And to start with, let's choose a basis of vectors for the space in which x lives. Let's say it's E1 to En. We can then write x as the following sum. We go from I equals 1 to n, and we expand x in coefficients which multiply the vectors of the basis. Then if you apply g to x, thanks to the linearity, we can consider the application of g to each vector of the basis and multiply it times the coefficients of the expansion of x. Finally, we can consider this last term here and defining a new basis in the space in which g lands after the application to x. We can expand this term and finally find our matrix multiplication. So let's define this basis. Let's call it epsilon 1 to m. And we can write this sum here as a double sum now of gij times xi times the basis vector epsilon j. And this gij term is the generic element of the matrix G, capital G, we are looking for. The simplest linear system that you can think of is a scalar linear system, which has the form x dot equals a times x. Now, if we look at this equation, we immediately see that the solution must be given by a function which is proportional to its derivative. And such a function exists and is the exponential function. So we'll have that x is some constant, which is preserved under derivation, times the exponential function e to the at. And to find the value of this constant, we need to look at the initial condition. So we assign x at time 0, and e elevated to 0 is 1, and so c must be equal to x naught. So we see that the solution to this system is an exponential function, which has different behaviors depending on the value of a. In particular, assuming an initial value x naught, we'll have an increasing exponential if a is positive. We'll have a constant function if a is equal to 0, and we'll have a decreasing exponential if a is smaller than 0. In the first case, we see that the system is unstable as the state diverges indefinitely as time goes on. In the last case, we see that the system is asymptotically stable as the state converges to 0 as time goes by. And finally, in the case where a equals 0, we will say that the system is just marginally stable or simply stable. Another famous example of a linear system is the harmonic oscillator. Let's write it down. We have the second derivative in time for x, which is equal to some negative constant times x. As we have seen, we can always stop at the first order of derivation by increasing the number of state variables. So let's define x1 and write x1 dot equals x2. And actually, let's add an omega here for simplicity. Then we can write x2 dot as the expression we have above divided by omega. We can also write this system in matrix form as x dot equals some antisymmetric matrix. If we prescribe the initial conditions to the system, well, it is well known that the solution is given by a combination of sines and cosines. So let's say x1 will be some constant time the sine of omega t plus some phase term, and x2 will be some constant times the cosine of omega t plus phi2, some other phase term. And note that these constants must be equal, because when we take, for example, the derivative of x1, what we obtain is c times omega times the cosine of omega t plus phi1. So to have that the derivative of x1 is proportional to x2 through the constant omega, as we see here, then both the constant terms and the phase terms must be equal. So actually we can also get rid of the index here in the phase term. Now, to find the value of this phase term, we can apply the initial conditions. So, for example, if we give some values to the entries in x naught, and by inverting these relations, we can find the values for the phase and amplitude terms. Now, it is worth to observe that the modes associated to the evolution of the harmonic oscillator are oscillatory modes, which never fade out. So, in a sense, their amplitude stays constant, as before in the case of the marginally stable system, the value of the state variables would stay constant. Let's see what happens if we add some damping to the system. For the damped harmonic oscillator, we have the following equation. The second derivative of x is again proportional to minus omega squared x, but now we add a damping term. And this damping term, for reasons which will be clear in a second, is given by the following expression. It's minus 2 times a coefficient denoted by zeta times omega, the frequency of the undamped oscillator, times the derivative of x. We can again introduce an auxiliary variable, so we denote x1 dot equals x2, and then x2 dot is just the expression above, where we replace the derivative of x with x2. And we won't go through all the calculations, but the solution in terms of x is given by the following expression. We have a constant, like before, then we have an exponential term, e to the minus zeta omega t, and then we have a sinusoidal term. Again, the constant c and the phase term can be determined based on the initial condition. And assume, for now, that omega is positive and that the damping factor, z, is between 0 and 1. Now, what is interesting is that if we look at the system in matrix form, we have the following. We have that x dot, which is the derivative of x1 and x2 in this case, has the following expression. It's 0, 1, minus omega squared, and minus 2 zeta omega times x. Now, if we look at the eigenvalues of the matrix that appears in this equation, what we find is the following. And typically the dynamical matrix of a system, of a linear system, as you've seen, is denoted by A. So these eigenvalues, which we can also sometimes call lambda 1 and 2, will be equal to minus zeta omega, which is the same as the exponent that appears here, plus or minus omega times zeta squared minus 1. But since we say that we assume that zeta is smaller than 1, we can invert this expression because the term under the square root is negative and add the imaginary unit here. And notice that the imaginary part of this eigenvalue is exactly the frequency of our sinusoid. Moreover, we can observe that if zeta were negative, then the exponential term would be diverging, while if zeta were larger than 1, then the expression under the square root in the eigenvalue expression would have been real, and then we would only have had real modes, so decaying or diverging exponentials. Meanwhile, the modes that appear here are as follows. They have a sinusoidal part with the frequency that we have just seen, which is damped by an exponential envelope. What we have just seen about the modes of a damped oscillator generalizes in the sense that for every linear system in the form x dot equals a times x, and for now we neglect the effect of the inputs, we will have natural modes which are linked to the eigenvalues of the matrix A. And in particular, if the eigenvalues are real, we have modes in the form e to the lambda t. While if lambda is complex, and in general for real systems we'll always have complex conjugate pairs appearing, we will have modes which have the form e to the real part of lambda times t, and then we'll have the sine or the cosine of the imaginary part of lambda plus some phase term. So we can immediately see that the system has stable mode whenever the real part of the eigenvalues is negative, while it will be unstable if we have at least one eigenvalue with positive real part. We can try to exploit what we have just learned to find a general formula for the explicit representation of a linear system. And this is one of the very few cases where we actually have an explicit representation. So to start with, we will need to generalize what we've seen about the exponential as a solution of a linear system to matrices of general dimension. And in particular, we will deal with systems which, as we have seen, have the form x equals a times x plus b times u. And for now, we just forget about the input to the system and just concentrate on the autonomous part of it. So to solve this equation, we would need a function which has the same property of an exponential, which means a function that is similar to its own derivative. So we define the exponential of a matrix, e to the at, and now a is a matrix, and the exponential of a matrix will also be a matrix, I will see. We define it as a function such that the derivative in time of e to the at is just a multiplied the function itself. And an expression for this function is easy to find if we have a diagonal a. So if a is diagonal, well, if a is diagonal, and let us denote it by a big matrix lambda, then basically what we have is a collection of decoupled scalar systems, just like the first one we have seen. So in this case, we expect, and we know it since we know the solution of a scalar system, that the exponential of this matrix will be a matrix with the exponential of the terms on the diagonal. And this is when big lambda is just lambda 1 to lambda n. Now we can also exploit the Taylor series for an exponential to rewrite this in a different way. So each term will become the Taylor expansion for the exponential. So the sum of this will be for lambda 1, and we'll have this sum for all the lambdas. And we can collect these terms so that our exponential of a matrix becomes the Taylor series of lambda to the k, t to the k, over k factorials for k that goes from 0 to infinity. And in particular, we define lambda to the 0th power as the identity matrix. Now, if a matrix is diagonalizable, then we can always find a similarity transformation that brings it into the form that we've just seen, which is a diagonal matrix like lambda. So we could write something like A equals t to the minus 1 times lambda times t. So let's see what happens to the exponential of a matrix when we apply it to a matrix which is linked to a diagonal matrix through a similarity transformation. So e to the at now will be the sum through our Taylor series, and from k that goes from 0 to infinity of t to the minus 1 lambda t to the kth power t to the k over k factorial. But notice that this term here, if we write it out in full, will be something like t to the minus 1 lambda t times itself, and so on and so forth. And all the terms t times t to the minus 1 will cancel out. So this will just become t to the minus 1 times lambda to the kth power times t. And hence, we can write our exponential as t to the minus 1 e to the lambda t. So if lambda is a diagonal matrix, we see that the collection of exponentials that appears on the diagonal of the exponential matrix of lambda is just mixed by this transformation matrix when we compute the exponential of a matrix which is similar to lambda. Finally, we are ready to derive our Lagrange formula, and we do it by decomposing the evolution of the system in a quite canonical way, which is in the free evolution and the forced evolution. So the free evolution is what we have whenever we consider the evolution of the system under the effect of the initial conditions, but without any input. So the system we are considering, which was x dot equals a times x plus b times u for x starting at x naught. Well, in this case, we'll neglect the effect of the inputs. And this is a problem we now know how to solve, because we know that the function that satisfies this relation here, that the derivative is proportional through the matrix A to the function itself, is just the exponential of a matrix. So the solution to this problem will be x of t is e to the at, and then, as in the scalar case, we can enforce the initial conditions by solving the problem at t equals 0. And this will give this product. Next, we will need to deal with the forced response. This is what we have when, in our system, we now consider the inputs but neglect the initial condition. So we set them to 0. So now we can write the following. We multiply the equation of our system times the exponential e to the minus at. And we bring the first term on the right-hand side to the left-hand side. Now we can recognize that the left-hand side is just the derivative in time of the function e to the minus at times x. And notice here that by the definition of the exponential of a matrix, its product with the matrix itself commutes. So now we can integrate this equation, and what we find is that e to the minus at times x is equal to the integral from 0 to t of e to the minus to the minus 8 tau b u tau in d tau. And we will also have an integration constant, but this constant will be 0 because of the initial conditions of the system, which are 0 as well. Now all we have left is to bring the exponential e to the minus at to the right hand side. So we multiply everything times e to the at, and we have x of t equals the integral of e to the at minus tau times b times u tau d tau. And this is the expression for our forced evolution, and the integral that appears in this expression is called a convolution integral, and it's sometimes expressed also as e to the at convolution product with b u of t. Now, putting all together, we have our Lagrange formula, which is given by x of t equals the free evolution of the system, e to the at times x naught, plus the convolution integral, e to the at minus tau, b u of tau d tau. And we can find a similar expression for y just by multiplying everything times c. So we obtain that y of t is c e to the at x naught plus the convolution integral of c times e to the a t minus tau b u of tau d tau, plus we have a term which is d times u of t.